matching problem. So, when we have got this fast ATE and this code testing is slower. So, this ATE can provide data at a higher rate, and then we have to have this testing to be done at a lower frequency. So, that is the problem of bandwidth matching. So, we have the ATE that has got a number of channels going out of it, and then some of the channels are high frequency lines. Like in this ATE, suppose there are 2 lines which are high frequency lines, and there are 2 lines which are low frequency line. And then we have got this. So, the overall ATE is it has got 4 pins. So, WATE equal to 4, the width of the ATE is equal to 4, and ATE frequency factor n equal to 4. So, frequency factor means compared to the core at what is the high frequency rate for the ATE. So, the ratio of the 2 frequencies is a 4. So, ATE is working at a 4 times faster than this core for the testing purpose, and number of high frequency pins equal to 2, u equal to 2, that we have just seen. Now, so W into ATE, so this formula has to be satisfied. So, W into ATE is the width of the ATE and multiplied by FATE. So, the number of bits that are transferred through this channel per unit time. So, that should be same as W into TAM divided by into the F TAM. So, number of bits which are actually reaching the core. So, they should be matched. Okay. So, there is naturally there is a mismatch here. So, if you just extend it, so this W into AT into WAT into FAT. So, WAT, so if you just expand it, so it is become this high frequency part that is operating at this frequency of ATE, and WTAM minus U. So, that is the number of pins which are operating at a lower frequency, that is operating at the frequency of this lower frequency TAM. So, this part does not create any problem. Okay. So, for this speed matching between this ATE and this core. However, the first part is going to be extended, because this FATE is n times F TAM. Okay, because this ATE is n times faster than TAM. So, I can substitute this FATE by n into F TAM. So, this becomes the expression becomes something like this. So, if you so W is n minus 1 into U plus WAT. So, if you solve this problem expression, then this will turn out to be this. So, W must be equal to n minus 1 into U plus WATE. So, that actually gives the expansion in the number of channels that we can get at the core end or the SOC end. So, this is the bandwidth matching part. So, which will be doing this thing. So, it will be increasing the rate at which this data is being fed to the channels. Now, this virtual TAM, so it has as if I have 10 low frequency lines to the cores. So, by looking into this formula, so n minus 1, so n is equal to 4 and u equal to 2. So, 4 into 2, that is 4 minus 1 into 2, that is 6, plus this WAT is 4. So, that is total 10. So, that means on this virtual line I have got as if the 10 low frequency lines to the cores. So, though there are 4 channels coming from the ATE, but for the scheduling purpose we see we have got 10 lines to be fed to the SOC. So, that makes it very flexible, like when I am doing this test scheduling. So, I can assume that whatever technique I am following, partitioning or bin packing, etc. So, that can take help of these 10 low frequency lines. So, how this will be done? So, this high speed from this bandwidth matching part. So, from the ATE we have got this U high speed lines. So, U high speed lines, so they are fed to a serial in parallel out register. So, these U lines are coming here, and then each of these lines are feeding this U number of lines parallelly. So, this U bit patterns are going parallelly to the core, and then this WAT minus U. So, that many lines are coming here. So, this part is generating U lines and this part is WAT minus U. So, that is fed here, there is a low speed TAM part. So, that is being fed to the core, and then this is actually this u lines plus w, so this u lines will again be converted via this parallel in serial out register, that will be converted into a serial value and that will be transferred back to the ATE. So, we have got this low speed ATE and low speed TAM lines here, we have got low speed TAM lines at this point, we have got high speed TAM line here, okay. So, which is implementing the bandwidth matching issue. So, the scheduling policy can be benefited by having this thing. So, how can we select this U and N, like how many high speed line and what is the frequency factor. So, testing SOC is often dominated by the testing time of bottleneck cores. So, bottleneck cores are normally, what is the situation, like if I have a core, then if this core is given more TAM width. So, it is say it is given say sometimes say with w equal to w1 and sometimes it is given w equal to w2. So, if w1 is more than w2, then the corresponding test time T of w1 is naturally expected to be less than T of w2. Now, we have seen that due to this Pareto optimality, this always does not happen. So, in many cases what happens is that T of w1 remains equal to T of w2. But in general, so we have got this staircase type of behavior. So, these Pareto optimal points are occurring at each of these points, okay. Sorry, this one, then this one. So, it occurs at these points. However, it may so happen that for some cores this Pareto behavior, this type of Pareto behavior does not exist. So, whatever be the TAM that we assign to this core, so it takes a huge amount of time. So, this may be due to some module, some code, some functional module inside the code that takes a huge amount of time, and it is not dependent on the maybe some scan chain has been kept there. So, which is very long. As a result, this whatever be the TAM line we assign to it, so it is going to be dominated by the length of the scan chain, and this assigning more number of TAM bits to the core does not help in improving its test time. So, that may be the situation, and that type of cores, so they are called bottleneck cores, because whatever be the amount of test time assigned to that core, test width assigned to that core, the test time of it does not decrease. So, total test time is of the SOC starts getting dominated by the test time of that particular core. So, this type of cores, so they are known as bottleneck cores. So, testing time of SOCs containing the bottleneck cores does not decrease for TAM width greater than some value W star. So, if you increase even if you assign more TAM width to the SOC, so then also it does not improve, because that bottleneck core, so it will stop the improvement in test time further. The lower bound on test time in such SOCs is T star corresponding to the TAM width W star. So, we cannot reduce the test time beyond this T star value. So, if I have as I got in my scheduling, so if I got some test time results which are close to T star, then we should be happy that we will not be able to beat this bottleneck this lower bound W T star. So, we have to be we know that perhaps we have reached the optimum solution for this particular SOC. So, these are some bottleneck cases, like say U226. So, this particular SOC code, they are all from that ITC 02 benchmark suite that we are talking about. So, U226, it has got a bottleneck at 48 bits. So, even if you increase its test time W width beyond 48, test time cannot be reduced. So, it remains at 5333. Similarly, D281, so there all it remains at 3926. That so, all these codes, all these SOCs have been mentioned here, and for each of them you see that there are some bottleneck core, due to which even if you increase the W star this TAM width beyond these W star bits, it will not improve the test time beyond this T star values, clock cycles in terms of ATE. So, if we try to find a relationship between this U, N and W star, then this u and n, they should be chosen such that the total virtual TAM width w does not exceed w star, because increasing beyond w star is not going to help. Okay. So, it is not going to decrease the test time for that code anymore. So, the virtual TAM width w, it must be less or equal w star, and again we know that w is given by this formula n into u plus w at e minus u, where n is the frequency factor, u is the number of high speed channels, and this is the so w at e minus u, that gives the number of low speed channels. So, that is the total TAM width w that we get in a virtual TAM environment. So, if you substitute it here, then we get u into n minus 1, it should be less or equal w star minus w at e. So, this way we can choose these values of u and n such that this constraint is satisfied. Okay. So, that gives us a guideline, like in a virtual TAM based environment. So, how many so maybe u is fixed by the ATE, number of high speed channels that it can provide. So, that is specified by the ATE. So, we can do a choice of this n, or if we have got this thing, if we have got that frequency relationship available, the speed, the frequency of the frequency factor between the ATE and the chip, then we can put that value and try to get what is the value of u, and the u should not that maybe ATE is providing a number of high speed channels, but we may not be able to use all of them. So, that is possible. So, we can go for, we can use them as low speed channels, and the remaining ones we use for high speed channels. So, this graph actually shows the variation of u with n. So, if you increase the value of n, this u value starts decreasing. Okay. So, this u into n minus 1. So, this is actually the plotting of that u into n minus 1 satisfying this relationship. So, if it is at this point, so n 1, so this is the corresponding u 1. So, this may be one choice, and beyond this it is not improving further. So, we can go for that. So, for u versus n for different ITC02 benchmark circuits have been chosen. Accordingly, the proper point can be chosen. So, which u, which n and which u should be used, that can be chosen by the test engineer by looking into different points. So, looking into the different graphs, so it can be chosen. Another possibility that we can have in the ATEs is known as multiple speed TAM architectures. So, multiple speed TAM architectures, they exploit the port scalability features of ATE. So, port scalability means that it facilitates efficient use of high data rate tester channels. Some of the tester channels are fast, some of the tester channels are slow. However, so it does not use on chip hardware overhead. Like in case of virtual TAM, what was required was that there was a requirement to have that bandwidth matching hardware. So, which will be doing this shifting and all that. So, the serial to parallel converters were necessary on the chip, so that we can do the speed matching between the between the ATE and this SOC, and using this virtual TAM environment. So, this will try to reduce the test time for this SOC by using some fast and slow channels. So, test time also gets reduced for the bottleneck cores. So, that is another advantage that we have in this particular policy, multiple speed TAM architecture. The basic idea is like this, that suppose we have got a dual speed optimization problem. So, this ATE has got V number of channels which can operate, whose data rate is high f into r, and this one it has got W minus V low speed channels. So, that is operating at a lower data rate r, and these are the embedded codes that we have. So, the problem is to determine the wrapper design for individual cores, TAM width and test data rate for each core. So, at which rate it should be tested, at lower at r, at a rate 1 or at a rate f. Okay. So, that is the rate has to be chosen, and the SOC test schedule such that total number of TAM wires utilized at any moment does not exceed W. So, that is always there. Then the number of TAM wires driven by the high data rate does not exceed V. So, this high data rate only V, and the low data rate remaining will be low data rate, W minus V will be low data rate, and the SOC testing time is minimized. So, these the first two are the constraints. Total TAM wires should not be more than W, and these high speed wires should not be more than V. So, these two are two constraints, and the optimization is to minimize the SOC testing time. So, how can we do this selection? Okay. So, suppose we have got this Pareto optimal distribution, like as we are increasing the TAM width at so this is the test time. So, at R data rate, so it happens to be like this. So, if the testing is done faster, then we see that this test time reduces significantly. So, this F into R, so data testing time will, so even if I use lower TAM width, so test time is even smaller. So, maybe for high for normal TAM lines, so I have to use some this type of TAM widths, because I beyond that this test time is quite high. So, I do not have any choice. So, I have to use this more number of low speed channels, but when I have got these high speed channels, then I do not need to use this higher number of channels, higher number of higher TAM width. So, the low TAM width may be sufficient, because the test time that we get is reduced significantly. Okay. So, I can use say some values in this range, so that it is done. So, core 5 of this particular SOC P93791. So, if you do this, if you are doing at a slower data rate, then this W minus V equal to 23. So, that if you put it on a slow channel, then it has suppose it has got 23 lines, then the test time becomes 11398.9 microsecond. Whereas, if you put it on a faster line, giving 10 faster lines, so it can test it at 14026.9. So, you see the number of TAM lines requirement has reduced from 23 to 10. So, remaining lines are available for doing something else, and this test time increase may not be very significant. Okay. So, from 11,000 it is increasing to 14,000, but in this remaining time we may be able to schedule some other tests, some other core tests, so that this test time becomes better utilized and overall SOC test time reduces. So, we can do some selection like that. So, maybe after so how to match these core scan frequencies to ATE data rate. So, we may decide that this core A and core B, so they will be operating at 40 megahertz, and core C and core D, they will be operating at 80 megahertz. So, what we do, we this core D we put it on say on this 40 megahertz line. So, this is W2, the width is 2, and we put it on a 40 megahertz frequency, and this core A, so they are put on W1. So, that W1 equal to 8. So, the width, the test width database is so test width is 8. So, this is the baseline case, that is I have divided the 10 lines of the TAM that we have into 2. The first one is 8, the TAM width is 8, and the second TAM width is 2. So, the schedule it generates is that core A is scheduled here, core B is scheduled here, core C is scheduled here, and core D is scheduled here. So, overall test time is T equal to 456 microsecond. So, it ends at this point. So, that is 456 microsecond. Now, in another case, so if we do the schedule in a slightly different fashion. So, what we do, we put this core C and core D on this 80 megahertz part with the width 8, and this in the previous example. So, both F1 and F2 they were 40 megahertz. Okay. So, they were none of them were put on the fast channel or the fast ports, but here I am putting this one, this W1 equal to 8. So, this C and D they are put on faster channels, and this A and B they are put on the slower channel. So, that way this C and D they were very big rectangles. Previously, if you see that they were very big rectangles C and D. So, this putting them on faster channel can reduce the test time. So, that is done here, the C and D they are put on faster channels. So, the test time reduces and this overall test time becomes 275 microsecond. Okay. Now, take another case where this W1 this distribution of TAM is done like this, the W1 is 5 and W2 is also 5, and then this W1 operates at this higher frequency 80 megahertz and W2 operates at lower frequency 40 megahertz. Now, this on this 40 megahertz I can on this 80 megahertz only core C and D can operate, but we put only core C here and core A, B and D all of them are put on this 40 megahertz frequency with W2 equal to 5, and then the test time reduces to 246 microseconds. So, in this way if we can match these core frequencies with this TAM frequencies and all that, then and do a scheduling properly. So, we can do very good work in terms of this test time reduction. So, what is the overall problem statement? We are given the test data parameters for n embedded cores. So, we have got their testing their test lengths, their test times and the frequencies at which they can be tested, and the Pareto optimal points are definitely required. The maximum scan frequency Fi star for each core. So, their frequencies are known at which it can operate. So that we do not do a violation. So, it is not that we put it on a frequency higher than that it can sustain, and the SOC level TAM width W. Then we have to determine the following: the number of TAM partitions. So, how many partitions we are doing. So, here interestingly, so here it is a partition based approach. So, it is no more a bin packing, because there the flexible TAM is not possible, because I have to the same TAM line it is not possible that sometimes it works as high frequency, sometimes it works at low frequency. So, the frequencies are same. Of course, within a TAM we can think about within a TAM we can think about this bin packing, and that may possibly be tried by first doing this type of assignment, and after that like we may try to improve that assignment by means of some bin packing. So, that may be there, but the basic first level solution it has to do with this this partitioned TAM. So, we determine the number of TAM partitions B, the width Wj and scan frequency Fj of each TAM partition J. So, at which what should be the TAM width and what is the frequency of that TAM, and then assignment of cores to TAM partitions. So, this is useful if the ATE has got the feature that certain we can tell that okay, this number of these lines we want to put on this frequency. So, the ATE has restriction like that how many out of the total W number of channels only V number of them can be put on say high frequency, but which V if we have choice. So, then this particular formulation is trying to capture that situation. So, otherwise we cannot have a choice of frequency for each TAM partition, but assuming that we have that choice. So, this Fj the scan frequency for the partition has to be assigned, and then the assignment of cores to the TAM partitions. So, this is the problem statement such that these things are met. The TAM frequency does not exceed the maximum scan frequency of any core assigned to that partition. So, as we have seen that if a core can operate maximum at 40 megahertz, we cannot put it on a 80 megahertz channel. Okay. So, that is there. Then the overall test time is minimized. The test time has to be reduced, and the sum of widths of all TAM partitions does not exceed W. So, this is the third requirement. So, that is from the physical point of view. So, second two points are second two bullets are fine, the last two bullets. So, they are for any problem, but the first part is important, that TAM frequency of a TAM it should not exceed the frequencies of the cores at which they are going to be tested. Solution technique. So, there are lower bound on test time based on geometric arguments, a rectangle packing. So, we can do a rectangle packing and try to see what is the minimum time. So, we can say that okay, it cannot be reduced beyond that. So, that is a lower bound based approach. Then there are some approaches that have been reported based on integer linear programming. So, they are actually trying to formulate this mapping problem using this integer linear programming that we have seen in the fixed TAM partitioning case. So, here also that can be extended. Okay. So, the only thing is that the frequency part will come as a result, some additional constraints will get added, but problem is that it is limited to small problem instances. So, it is that way the ILP, the basic problem is that it does not work if we have got large number of equations, large number of constants or large number of variables. So, it cannot be done beyond that. So, for small sized problems it works, but it gives exact result. So, we may be interested in that, and there are some fast heuristic methods that have also been proposed that gives rise to scalable close to optimal results. So, that they have also been done. So, basically the heuristics that have been used for the problems like PAW, PAW and NPAW. So, they have also been used for solving the problems under this category, because what extra thing that we need to do is to do the frequency assignment part. So, accepting that rest of the things are same. So, they can be used as well for doing this partitioning of TAM and assignment of cores.